Vision-aided dynamic exploration of unstructured terrain with a small-scale quadruped robot. Our list of authors, many of whom is affiliated with MIT and UMass, explored how effective sensor integration, dynamic locomotion, and jumping can be integrated in a small quadruped robot. In this paper, they outline the difficulties of legged and small robots, such as space limitation with sensor placement. They highlight how leg robots are well suited for rough terrain locomotion compared to wheel and track robots. And despite the limitation of smaller robots, they are useful to maneuver through narrow paths and gaps. So combined, a small quadruped robot is useful in areas such as disaster response and rescue scenarios. As shown, the author designed a series of environmental challenges, such as cluttered terrain, obstacle, and stack panels. Each task was repeated in isolation before this legged robot was able to overcome all the obstacles in a single run. Let's dive a bit deeper to understand how this was achieved. The platform used in this study is the MIT Mini Cheetah, which weighs about 9 kg and is 0.3 meter tall. This is an electrically actuated small-scale quadruped robot. To gather visual data of the environment, the researcher opted to use 2 Intel RealSense sensors instead of using a large LiDAR. The front camera provides depth images, which was used to construct a map of the area, while the top camera served for localization. This RealSense tracking camera is connected to the Intel upboard computer, which was running Linux, while the front depth camera was wired to an external desktop because of the unstable computation speed from the point cloud data stream in. Because of this connection, the Mini Cheetah was always tethered. Just a quick glance of the sensor used. Both of these RealSense cameras are small, has a wide field of view, and high frame rate, making them a great option for mobile and highly dynamic robotic applications. The software framework consists of 3 main components. The visual processing, which is responsible for outputting the robot position and orientation, as well as a labeled height map. This localization information is sent to the height map construction program, and the real-time locomotion controller, which is used to visualize data to adjust the direction of walking and step location of the robot. The motion library saves pre-planned motion such as jumping and recovery stand-up protocol. Once a predefined motion is called, the saved joint position and trajectory are sent to the actuator controller to execute the commanded behavior. This software was optimized with efficient memory handling and data downsampling so that it can be run on the onboard Intel computer. For the height map construction and filtering, a morphological transformation was implemented using OpenCV. This is an example of a 3D point cloud graph representing a set of stairs. Moving from left to right, the raw height map is filtered and the gradient is computed. The value of the gradient is used to segment the terrain by traversability, namely, steppable, unsteppable, jump only, and so on. In this figure, the robot moves back and forth by following the given trajectory, and once it detects an object, it goes around the obstacle autonomously. This obstacle avoidance is achieved with the use of potential field algorithm. The robot can smoothly avoid obstacles without need for explicit low-level path planning or prior knowledge of the terrain. To achieve the stable and robust walking motion control, the researcher implemented a hybrid control scheme consists of 2 controllers, MPC, Model Predictive Control, and WBC, Whole Body Control. With gradient-based height map evaluation, you're able to calculate the footstep planning, or where should the robot place its foot as it moves to the next neighboring grid location. This search is done iteratively. Once we find a proper place to step as determined by the traversability map, we read the height of that point and adjust the robot landing based on the height of that step location. Finally, in addition to the walking controller and ground obstacles, the Mini Cheetah had to overcome obstacles that is too high to step over. Thus, the researcher implemented jumping motion for these scenarios. To achieve this, an optimization library was generated. It consists of a set of joint state and torque for each time step of the trajectory, including a set of predefined contract states. In conclusion, this small quadruped Mini Cheetah was able to successfully track a specific path, see and build a map of its environment, plan and execute safe footstep on and over obstacle up to 10 cm tall, recover independently if it had fallen, identify obstacles which it could not traverse, and modify its path to avoid them, and finally, jump onto a platform. If you're interested in working with this Mini Cheetah, then the author hopes that this paper will encourage further development in the field of control, perception, and autonomy for highly dynamic legged systems. They hope that the next mini cheetah platform will be an untethered system. Credits to the author for all the visual. Thank you.